If we are using a vector function to parametrize a curve, its derivative can show the tangential direction of the curve. On the other hand, if the vector function describes the position of an object varying in time, its derivative is the velocity of the object. But we need to dive a little deeper if we want to actually calculate those things. This is calculus with Python with derivatives and integrals of vector functions. The derivative of a vector function r of t is calculated by taking the limit when delta t tends to 0, and this vector might be interpreted as the velocity of the trajectory. If r of t describes some trajectory and delta t is a small interval, then r of t plus delta t minus r of t is the displacement from instant t to instant t plus delta t. When we divide this displacement vector by delta t, we rescale the displacement vector, getting an approximation to the displacement per unit of time. Another way to understand the derivatives of vector functions is to think of these displacement vectors as the direction vectors of a secant line to the curve parametrized by r, through r of t plus delta t, and r of t. In this case, the limit gives the direction vector of the tangent line to the curve, if it is not 0. Luckily, these limits can be calculated by taking the derivatives of the component functions that we know from single variable calculus. Check out a proof of this and an explicit example at the book in the description links. Often, r prime of t is called the tangent vector to the curve C. We must be careful, because if r prime of t is equal to 0, then the curve may not even have a tangent, even though r is differentiable. For example, the curve parametrized by t cubed, t squared, is differentiable for all t, but it does not have a tangent at t equals 0. This happens because r prime is 0 at this point and sharp corners might be hidden under such points. We say that a parametrization is smooth if it is differentiable, and if its derivative is different from 0 at every point. A curve is said to be smooth if it admits such a parametrization, and it is easier to work with such curves. For a smooth curve, we can define the tangent line at r of t as the line through r of t in the direction of r prime of t. This equation parametrizes the tangent line at r of t with the parameter u. Check out the codes in the description links and plot some tangent lines for curves of your choosing. Oversimplifying, we can say that the derivation rules for vectors functions are the same as the derivation rules for single variable functions, with some form of the product rule for the inner product, and for the vector product of two vector functions. Check out the theorem in the interactive book for more on this. We can also integrate vector functions component-wise, and have primitives of vector functions. This is important for trajectories. Often we might know the force an object is subject to. If we integrate from 0 to t, and input the velocity at t equals 0, we find the velocity of the particle. Integrating once more, and inputting the initial position, we find the position of the object at every instant. The codes calculate definite and indefinite integrals of vector functions. Thank you so much for stopping by. If you like the content, please give us the thumbs up. Check out our codes in the description links, and share this video with your calculus interested mates.